Hi, everybody, and welcome to this presentation. My name is Alex Objulian. I'm a principal developer at Paddy Power Betfair. And I'm joined today by my colleague, Raresh Russo. He's also principal developer. We've been both in the company for more than 10 years now, and we are based in Cluj-Napoca, Romania, a lovely city in the heart of Transylvania. First, let me start with a few words about us as a company. Paddy Power Betfair is part of Flutter Entertainment Group, and we are a global sport betting, gaming, and entertainment provider. Our mission is to bring entertainment to life for our customers in a safe, responsible, and sustainable way. In the past 6 years, we've been part of the team building a system from scratch, turning it into the world-class platform for operating promotions. One of the goals of this platform was to bring the personalization and real-time customer experience to a whole new level for over 7 million active customers. Achieving this was challenging, and considering the massive load we have to deal with, especially during popular sports events. Just to give you an idea, a single product called Betfair Exchange generates more transactions than all European stock exchanges combined. Today, the platform powers 3 brands, Paddy Power, Betfair, and FanDuel, and we are extending it to other brands of the group as well. Most of the ideas presented today are influenced from the experience we gained while building this platform. And we hope that you'll find it interesting and useful. Well, how would you describe a large majority of customers today? You can say impatient, in a hurry, with short attention spans, with the desire to experience pleasure or fulfillment without any delay. Designing an application which provides the real-time experience can lead to better customer acquisition and retention rates, improve customer satisfaction, and increase the chance of success for your business. So how does a real-time application design look like? Any success story starts as a monolith, also known as a monolithic architecture, meaning that we put all the functions of an application into a single archive package to deploy and run. Usually, this kind of application uses a single database and to store business-related data. Achieving real-time of this type of application is easy, given any interaction of the system is synchronous. Any customer action is reflected immediately in the underlying database, and the system can return the updated results taking into consideration previous actions. As the application evolves and matures, the number of features grows, so that the size of the code base and the number of teams involved in the development. Still, single monolithic code bases do not scale to large number of users, and crucially to large number of developers. Operating in many markets, each with unique requirements, will someday need many teams, each working on different areas of the product. So these teams will need to control their own development, deployment, and scale without having to coordinate the changes with other teams. In short, the development process needs to be distributed and decoupled, just like our software. Let's assume we want to break the monolith. The first attempt lead to microservices deployments communicating through a shared database. And this becomes extremely inconvenient in the sense that the shared schema of that database tends to lock the versioning of the service. So if you change one thing that involves schema change, you'll have to change every other service relying on that schema. It can lead to situations when you have to sync the releases or to do them in particular order. So even if the services are separated, you cannot independently evolve or version them. The next milestone in the evolution of the architecture is having services that don't share a database. There are two types of communication patterns between services. The first one is through synchronous API calls using some kind of RPC mechanism like gRPC or REST. That allows easier to independently version services and doesn't have this locking through a shared schema. But it creates a greater problems like service discoverability or failure cascades. The second communication pattern between microservices is asynchronous communication. It is also called reactive or event-driven. Instead of point-to-point communications, it allows you to multicast messages to various services at the same time. The primary benefit of this communication pattern is the evolvability of your architecture and ability to create new services or update existing ones very easy. The technology behind this type of communication is usually a message broker. In our organization, Kafka is our technology of choice for messaging. Currently in production, we have several clusters with hundreds of topics through which billions of messages are flowing on the daily basis. Zooming out, the system we are working on might end up looking something like this. And of course, keeping a system real-time is a challenge in itself. And in case of event-driven communication, it boils down to making the consumers as fast as possible in order to cope with the overwhelming amount of data flowing through your system. Now, let's get back to the real-time aspect. How can we measure it for a complex system using asynchronous communication based on message queues? We can use an interesting analogy with a shopping checkout at a supermarket. Each customer staying in the queue is like an event. Using this analogy helps to understand what exactly real time is. In a perfect scenario, customer doesn't have to wait in a queue at all, and his perception of real time is great. However, during peak hours, the shopping experience degrades significantly because of the time spent waiting in the queue. One possible way to measure the real time is by the size of the queue. Consumer lag is an indicator of how much lag there is between producers and consumers. By observing the lag, we can be alerted when a certain threshold is exceeded, indicating there is a potential problem. However, this metric can be misleading because it doesn't take into account the time factor. In other words, even if the shopping queue is long, it doesn't necessarily mean that you'll spend a lot waiting in that queue. The opposite is also true. Short queue doesn't necessarily mean that the waiting time will be short as well. A better metric to measure the real-time perception is the max time spent by a customer waiting in the queue. This metric gives you the worst case perception. Now, imagine a queue of 10 customers. If on average each customer is served in about 1 minute, the last customer will have to wait about 10 minutes. And any delay or problem like an issue with POS, for instance, while serving a single customer can increase the waiting time of the rest of the customers from the queue. Of course, processing an event doesn't take a minute in our system. Most of the time it takes milliseconds. However, the same reasoning applies here as well. And any problem during consumptions like downstream errors like database outages or network glitches leads to a degraded throughput and increased waiting time. Well, the next question is what can we do to minimize the waiting time? Keeping the shopping checkout analogy is the easiest solution to increase the number of cashiers. This is equivalent to increasing the number of partitions for a topic. However, this approach has its limitation, like it cannot use uneven distribution of the load, or it has a physical limitation, like in supermarket where the space is finite, and you cannot have more cashiers than the space can allow. The same applies for partitioning of a topic. This limitation does not allow leverage the entire processing power, assuming the application cluster has a large number of nodes in order to cope with massive load. To overcome the above limitation, we adopted a hybrid approach that involves the database of our choice, Couchbase NoSQL. And how this hybrid solution works? By measuring the waiting time of an event, when a certain threshold is passed, instead of continue processing event, it is persisted to Couchbase as a virtual topic with unlimited number of partitions. This is like transferring customers from cashier to a self-checkout station open on demand, thus bringing down the worst-case perception of the time spent in the queue. You might ask, why not always use this? Why not always process events this way? Well, the reason is that it comes with certain costs, like increase in network traffic between application and the Couchbase server. Also, it has some fixed time delay due to indexing of newly added items. By using the hybrid approach, we managed to achieve the following. Great real-time perception during non-peak hours, usually less than 1 second, and leverage the entire cluster processing power during peak traffic. Anytime a delay threshold is detected, the secondary mechanism is activated. Thus, all the nodes of the services are participating in handling the load. And this way, by keeping the perception of real-time reasonable. Why did we choose Couchbase? Well, because it has a built-in support for the following key features, like it is distributed, it is scalable, it's very fast, and it's easy. The most important feature in context of our problem is the performance. These metrics are from our production system. The image from the top is showing the number of operations per second observed during the replication between two data centers. And highlighted in red, you can see we witnessed over 1 million transactions per second. The second image from the bottom is you can see the throughput achieved by a single virtual machine during an intensive workload. And you can see that on single VM, we noticed over 10,000 transactions per second while dealing with some intensive load during peak hour. These numbers are quite impressive and provide for us enough confidence to build a large-scale system dealing with massive load. Here is another example from production showing the hybrid approach in action. In this scenario, there was a massive spike of events that caused an increased lag in processing. The hybrid approach mechanism activated by transferring a large part of events to Couchbase in order to leverage the processing of the entire cluster. This helped the system to cope with processing of over 500,000 of events in about 3 minutes. Not having this mechanism would lead to a recovery that will take much longer. There are various scenarios when this situation can happen, like the system needs to recover from a temporary failure, which leads to an accumulation of a large number of events. Another example is there is a sport event that triggers some reward that needs to be paid out to thousands or hundreds of thousands of customers in a short period of time. Well, to sum up, the key takeaways are the real-time aspect is crucial while designing the successful application because it can lead to improved customer satisfaction, acquisition, and retention. Designing a real-time application is challenging, but using the right technologies can help. In our case, the combination of Kafka messaging and Couchbase NoSQL technologies fits very well. By designing a hybrid solution using secondary processing mechanism that is enabled anytime there is a degraded perception of real time, we managed to cope with massive spikes and reduce the number of complaints from customers during busy sport events. And I would like to end my part of presentation with a quote from Gall's law, which is quite well known. States that a complex system that works is invariably found to have evolved from a simple system that work. Thank you, and I'll go to you, Raj.
Thank you, Alex. I'm Raj Rusu, principal developer with Paddy Power Betfair. Good to have you here at Couchbase Connect. So what I'm going to talk about today is the way in which we have used Couchbase in Paddy Power Betfair to develop our promotional platform. We have a long history of using Couchbase as the solution, the storage solution for our promotional platform. What we mean by this is we have developed a system that is able to track the user activity, the activity that happens on our systems, and we have what we call mechanics. Mechanics being actual encapsulations of user behavior. An example of this would be if somebody makes a deposit on our site, we call that a deposit mechanic. If somebody would bet on our site, that's a betting mechanic. We have, as part of any promotion, we have two types of mechanics. One being what the customer does, and the other one being what we do. So it's a you do something type of interaction, and we give you something. So Couchbase has been very helpful to actually allow us to model different kinds of interactions in a kind of singular and unitary way. More precisely, we have initially started with developing a simple type of reward. Like we require the customer to do an action, as I was saying, maybe a deposit action, and as a result of that action, we are giving the customer a reward. This reward has been modeled as a Couchbase document with certain attributes, like what amount, it is a monetary amount that can be spent on our systems. Then, as a business requirement, we were asked to evolve this, and as you see here on this page, this is a game type of reward. So in the first example, the reward would be guaranteed. So you are guaranteed that as a result of your depositing, you would get the £5 reward. But in here, it's more like a lottery. So as a customer, you do something. In this case, it's a very simple action of just pushing this pinball button. And what you could do is actually a prize draw. So you could get any of the rewards that are configured on this prize draw. Unfortunately, yes, you cannot do. There is a chance to actually not win anything on this pinball. Where Couchbase has been helpful for us here is to actually allow us to evolve from a simple kind of reward to a more complex interaction where any of a particular bucket of reward can be awarded to a customer. Some other examples of such interactions would be what we call prize ladders and tickets. As part of another type of promotion, a loyalty type of promotion, we are able to, again, using Couchbase, to model a reward of a type ladder. So when the user first or the customer first does say a £5 bet, we advance the customer on the ladder on the first step. If the activity continues and the customer does another bet and so on, he can be advanced to the second level of the ladder. As a result of this promotion, you are being given the biggest reward that you have achieved on this ladder, and again, this is an extension from the initial modeling that we have used using Couchbase to this kind of ladder-based modeling, and The last example would be something that we've been able to do when the customer would interact with one of our promotions. We could release a ticket, so not an actual reward, but more like a registration number, and this ticket would then be used by a customer on external systems, such as maybe on TV shows, where there would be a show, and as a result of that, it would be a prize draw, and the customer could actually see their ticket winning on that TV show. The idea here is again the flexibility that NoSQL modeling offers, allows us to keep adding various interactions that are required by our commercial team and business teams. At the same time, being able to integrate on top of the same system. So these interactions are very different from a customer point of view, and they have been easily fitted onto the same set of core systems. Moving on from here, we have. I'm going to talk about some internals from this system, such as monitoring, which is a very important aspect in everything we develop at Paddy Power Betfair. Using Couchbase, you get for free, like out of the box, dashboards and metrics that tell you insights about how the system is behaving, and this is very good. These operational teams and on-call teams are using this to actually get a feedback on how the system is looking. But we have our own set of monitoring tools, like internal tools that we use to track activity and to gather metrics from our own systems. And we had the requirement to actually integrate Couchbase with our own monitoring tools. So we have been able to do this because of the REST APIs that are offered by Couchbase. So the way in which we did it is we have developed scripts that are running on our Couchbase instances, and they are pushing periodically all sorts of metrics that we are gathering from the Couchbase nodes. They are pushing these metrics into our tracking database, so it's a time series database, OpenTSDB. And whenever, say, an on-call engineer or a developer or DevOps engineer wants to have a look at how these metrics are looking, how do they correlate with other behavior, we use a visualizing tool called Grafana. So Grafana just pulls data out of this database instance, and we are able to have metrics on how the system is behaving, so on how Couchbase is doing. And the advantage is we are able to correlate the Couchbase activity with our own systems or with other applications, so that on top of the built-in monitoring, we are able to benefit from this REST API exposure for metrics. Besides monitoring, what we also use, and Couchbase has offered, is the alerting capability, which again comes already built into Couchbase. In this example, we are looking at a dashboard that shows the replication status. We are using a dual data center topology, so we are replicating data from a data center to another. And in this case, you can see here what Couchbase offers out of the box for the replication status. Like you know if there are any errors, you know if the replication is active or is paused. So this is very interesting, and it gives you an instant view on the system. We have used, again, based on the REST APIs that are offered by Couchbase, we have extended this to actually integrate such alerting into our own alerting pipeline. So I have detailed here the two clusters that we use. So this is from the first data center cluster. This one is from the second data center. They are having an active replication of data between them. And what we have done is, again, writing a small piece of code to actually make use of the Couchbase endpoints. We are querying, like, what's the status of the replication. We are doing this from an external monitoring system, which we call Sensu. This is the system that we're using. So this periodically checks, like, is the replication active? Is it error-free? And if everything is fine, no problem with that. Whenever there's an error reported or some malfunction on this replication, we need to know, because our systems depend on the data integrity between the two data centers. So at any given point in time, we want to know that we have the same data in both data centers. So in such a case, when something is reported as being not as expected, an alert is triggered. Depending on the severity of this alert, it can be direct phone call to the on-call engineer if the replication has stopped. So somebody needs to intervene. If it's not so bad, or if it's not on a critical system, this can be also transformed into maybe an email. So we have made great use of these features, because they integrated so well and easily with our own existing toolbox, really. The last thing on my agenda is what we call the active passive switch. It has to do with the dual data center topology that I've already mentioned. So we are running applications in two data centers, and we are doing this in an active manner, meaning a request from a customer, whenever it comes, it's being routed to either one or the other data center, and it's being routed alternatively, like on a round-robin fashion or according to other criteria. But we have to ensure that both data centers are active and are serving live traffic. So what we have done, so the first iteration was for the applications to write locally in their local data center, and have a cross data center application. So the feature offered by Couchbase, have that replicate data between the two data centers. However, on the promotional platform, we have seen this might get us into trouble, because if the same or if an activity happens for a customer, we could actually process activity for a customer at the same time in both data centers. This can be due to the asynchronous nature of our platform, and we could end up in the situation where we would have a conflict, because the same document would be modified on the first data center and on the second data center, and we are not able to make a call whether as to which modification to keep. So because of this requirement, we have actually evolved this active interaction with Couchbase into an active-passive switch. So we have added a layer on our applications to actually instruct the application as to which cluster we are now considering as active. So we have like stopped writing on locally and decided based on a configuration file that we keep in Couchbase, we decide which one of the two data centers is active. So using this configuration, we operate in an active-passive manner when it comes to our database, so to Couchbase. So some closing notes from my presentation is using Couchbase and using the NoSQL modeling, we have been able to build a platform that can easily model new interactions. We have been able to incorporate a large variety of interactions on top of the same core services. Also using the support for monitoring and alerting that is available in Couchbase, we have been able to integrate those as part of the alerting and monitoring pipelines, and we have been using the replication features, the data replication features. We rely on those, and again we have been able to alter and to integrate these replication features into our own systems and use those according to our own needs to actually keep data integrity and performance concerns to the required levels. That's all from me. Thank you very much for watching, and hope to see you soon.